Sample exam 6, problem number 27. Let X be a single observation from a distribution with probability density function f of x given theta, provided there. X 0, 1 to infinity, theta greater than 0. Which inequality below determines the likelihood ratio critical region for testing the null hypothesis that theta is equal to 2 against the alternative hypothesis that theta is not equal to 2. Problem number 27, we want to find the rejection region, and it specifically says to use the likelihood ratio test. And there we're going to reject if this ratio is less than k. And the top is the likelihood that it's maximized over the null hypothesis, and this is maximized over the entire space. So here is the likelihood, and we're given a single observation, and so now we take the log of it, and we get this, take the derivative. That implies that our maximum likelihood estimator of theta is 2, and that is going to be for the bottom. Now the top, the null is a simple hypothesis, so we just plug in that value. It's maximized at that value, which is 2. So we plug in 2 to our theta, and here we plug in x. So now we start simplifying, we get this. And then those can be combined to this, and then e of minus 2 is really another constant, so that can be divided to the other side. But if we do that, we can't call it k, so we call it, say, c. And so whenever this value is less than some c, such that, it makes it 0.05, or that's k is determined that way. But anyway, this is the rejection region. Number 28. The number of traffic accidents per week in a small city has a Poisson distribution with mean equal to 3. What is the probability of exactly 2 accidents in 2 weeks? Now 28, we're given that that within 1 week it's a Poisson distribution with 3 events, mean 3. But now we want to look at the traffic accidents within 2 weeks. So we're actually adding 2 weeks, and the sum of Poissons is Poisson, and you add the lambda parameter. So if we let y equal this sum, then it's Poisson 6. And we want to know the probability that it's exactly 2, so we plug in 2 to our lambda parameter and a Poisson, and we get 18 e to the minus 6. Number 29. Let x1 through x10 be a random sample from a normal distribution with unknown mean mu x and an unknown variance sigma x squared greater than 0. And let y1 through y6 be a random sample obtained independently from a normal distribution with known mean mu y equal to 0 and unknown variance sigma y squared. The statistic w, which is the sum of xi minus mean squared divided by the sum of xi squared, is to be used to test the null hypothesis that the variances are equal versus the alternative that the variance for x is greater than the variance for y. If h0 is rejected when w is greater than c and the significance level of the test is 0.05, then c must equal. Number 29, we have, they're given a w that is greater than c, and we want to, the alpha level is 0.05, we want to find out what c is. But before we start, let's do some background here. This sum here over the variance of x is actually chi-squared n minus 1, which is 9. And notice that we don't know the true mean here. So some people say that, well, we lose a degree of freedom because of that, and it's kind of a good way to think about it. So it's 9. Here we know the mean, so we're subtracting by 0. so we don't lose the degree of freedom. So this ratio is chi-squared 6, and that's n. So to be an F, and note that the x's and y's are independent. So when we create this ratio here, this chi-square distribution divided by its degrees of freedom, all divided by this chi-square distribution divided by its degrees of freedom is an F distribution. Okay, so now under the null hypothesis that our variances are equal, those cancel out, and then you take the reciprocal and we get this here. Okay, well, this is the value of W that they gave in the problem, this ratio. So W is 2/3, W, 2/3 times W. So, and then this was greater than C. So if we look at the rejection region, and F of 0.059 is 6, numerator, denominator, degrees of freedom, we get this. So we reject when this value is greater than 4.099. But the problem says W greater than C, so we have to take this to the other side, which implies that C is 6.15. Number 30. Figure A shows the probability density function of two symmetric bounded distributions with the same median. Which of the following statements about the means and standard deviations of the two distributions are true? Now, number 30, because the distributions are symmetric with the same median, and that is also important, the means are the same. And then if you look at the distributions, more observations are farther away in the distribution 2. So that tells me the variance is greater than 1. So the answer is D. And I'm going to see if I can flash this back here. So when we're taking the average distance from the mean, this distribution will have a larger variance because the majority of them are out here. And here the majority is closer. And the average squared distance, adjusted for unbiasedness, is the sample variance. Or the variance, so that's why this is bigger. Number 31, let x1 through xn denote a random sample from a normal distribution with variance sigma squared greater than 0. If the first percentile of the statistic W is 1.24, where x bar denotes the sample mean, what is the sample size? N. Number 31, W is chi-squared with n minus 1 degrees of freedom. And so we want to know the chi-square 0.01 with some degrees of freedom is equal to 1.24, which then you go on the book, and it says that with 7 degrees of freedom you get this, but then that's n minus 1 degrees of freedom, so the answer is n equal 8. Number 32, let x1 through x4 be a random sample from a distribution with density f of x given there. For x greater than 4, where beta is greater than 0. If the data from this random sample are 8.2, 9.1, 10.6, and 4.9 respectively, what is the maximum likelihood estimator of beta? Number 32, we're finding the maximum likelihood estimator of beta. So here is our joint distribution of our data, 1 through 4. And this is each xi has to be greater than 4. Now we take the log of it, we get this. We take the derivative with respect to beta, we get this. We set it equal to 0. We solve and we get beta is actually the sample mean. But this can, well, minus 4. but this can be the 4s over this and the 4s over that. And you end up, you can simplify it to this, and then you plug in all the data that we have, find the mean, subtract the 4, you get 4.2. Now, one thing to remember when you're dividing this into 4, it's actually you're summing 4 of those 4s, which is 4 times 4. So when you divide by 4, it cancels and you get 4. Number 33, let x1 through xn be a random sample of size 2, or at least 2, from a Poisson distribution with mean lambda. Consider the following 3 statistics of estimators of lambda. Which of these statistics are unbiased? Number 33, which are unbiased estimators of, consider the following statistics. Oh, which are unbiased. So we know that the mean of x is lambda and the variance of x is lambda. And so for number 1, the sample mean is this, and you take the expectation in, and then the expected value is lambda, but you're summing n of the lambda, so that in lambda, one of the cancels with that n, you get lambda. So that's an unbiased estimate. Now notice that the sample variance is an unbiased estimator for sigma squared. And so when we plug in the sample variance, which is this, and then that's number 2, we know that that is sigma squared, which is lambda. Here, you take the expectation in the linear combination here. You get 2 this minus expected value that, so that's lambda. And that's lambda. 2 lambda minus lambda is lambda, so the answer is D. Number 34, a factory makes 3 different kinds of bolts, bolt A, bolt B, bolt C. The factory produces millions of each bolt every year, but makes twice as many of bolt B as it does of bolt A. The number of bolts C made is twice the total of bolts A and B combined. 4 bolts made by the factory are randomly sampled from all bolts produced by the factory in a given year. Which of the following is most nearly equal to the probability that the sample will contain 2 of bolt B and 2 of bolt C? Now, number 34, this is a classic multinomial setting, but the first part is you have to figure out the probability of each of the bolts, and the problem says that the number of bolts for B is twice the number of bolts for A, so you get this relationship. And then it says C is twice the number of bolts that A and B are made. So the way you do that is if you say, all right, what if we made 1 bolt? That means we'd have to have 2 B bolts, and if that's the case, so 1 and 2 is 3, and 2 times that is 6, so we'd have to have 6 C bolts. So that's 9 bolts, total. So the probability of A is 1 over 9, probability of B is 2 over 9, probability of C is 3 over 9. So that ratio will be the same no matter how many bolts we pick. If we pick 10, if we start with 10 or 20 or etc. So the number of bolts, because millions are made, it's essentially a multinomial with N and probably A, B, and C. So the problem asks, we want 0 A bolts, 2 B, and 2 C. So you just plug it into the multinomial distribution formula, simplifies to 32 over 43.